Thank you. All right, so I'm a postdoc currently at UW, and in a few months I am going to the University of Maryland as faculty. This work was a collaboration with some students, Peitong, who is in the second row, and Zach and Donna, who are also students at MIT, Remco Chang, who's a professor at Tufts, and then Mike Stonebraker, who was my advisor for my PhD at MIT. All right, so it's pretty clear that over the years we've been seeing more and more visualizations popping up on the web, even at web pages like the New York Times, like on the New York Times website, I mean. But, you know, what does it mean to actually go and try to quantify usage of visualizations on the web? It's cool to see that they're all over the place, but we're researchers, right? What does it mean for this to be popular? What does it mean for there to be a lot of visualizations? And when I talk about quantifying usage, I mean, you know, what are the variety of visualization types that we see, and how many observations do we see for each of these different types? And for example, on these different web pages, what are the different visualizations that you see per page? And in this work, we focus on scalable vector graphics. But your immediate reaction might be, why? Why vector graphics only? For example, here are two PNG files I found just through a really quick Google search. And obviously, they're just a lot of images on the web, a lot of visualizations on the web in a lot of different formats. Well, it happens to be the case that they're actually just a lot of images on the web. So if you don't restrict yourself at all, you have to weed through tons of images where the vast majority of which are not actually visualizations. So with SVG, we have this nice kind of filter because a lot of the visualization tools that people are using in browsers have SVG, Scalable Vector Graphics, as a prominent output format. What is up with the mic? I have to speak farther away from it. Okay, so is this better? Okay, perfect. All right, so what are the contributions of this project? So to sum them up really quickly, we crawled millions of pages and found tens of thousands of visualizations, over 40,000 to be a little bit more exact. And a lot of these examples are from real users, not just, you know, gallery examples from D3 where you're like looking at exemplars. And we automatically labeled these tens of thousands of visualizations by type using basic statistics over SVG elements combined with a machine learning model. And we analyzed this annotated corpus and found some really interesting insights, such as the majority of visualizations that we observed were covered by 4 different types that are pretty basic. But more obscure visualization types were used more when there were examples of how to use them available. Okay, so another question you might be asking is, why not just have manual data collection rather than this fully automated process, which is what we developed in Beagle? For example, why not just have people go to web pages and then point to the visualizations that they see and then tell you what visualizations they saw? And then you could turn this into a crowd-based model instead of an automated one. Well, the problem we found is that this manual approach just takes a lot of time and effort. So right off the bat, if you just hand random web pages to people and ask them to label visualizations, they'll be pretty good at labeling, say, this core set. Here, bar, line, scatter, map, maybe a couple more. But when you're just mining visualizations from the web, you see way more than this. So here are examples that we mined using Beagle from just D3. 22 different visualization types here. And people were pretty bad at labeling them without any kind of training. So in order to get people to do this right, we would have to train them all first. And that seems pretty cost prohibitive compared to, say, training a machine learning model to do a similar technique, which is basically classification of images, which is a really popular problem for applied machine learning. So then that's basically the premise of Beagle. We developed 2 major components, a web crawler, which goes to different websites and then extracts SVG files, an annotator that takes these SVG files, calculates basic statistics over them, and then feeds these statistics into scikit-learn, basically an off-the-shelf machine learning model, and then we store this data in a database management system so that people can actually query it. So for the rest of the talk, I'm only going to be talking about the crawler and the annotator, since those were really the major contributions of the work. Okay, so when it goes to actually mining the web and trying to extract visualizations, this is a pretty hard problem. And the big issue that we ran into with this work is that, you know, we actually crawled 20 million pages, but we were only able to find like 10,000 visualizations from that crawl. And it's because of this problem where the web just has tons of images that are not visualizations. And to give you a better sense of what we ran into, for every 2,000 pages we would visit, we would find one visualization. So we were working harder and not smarter in this case, and it was really costing us in terms of time. This also took months to do. So, working months to get just a few visualizations is a huge pain in the butt. So what we did instead was we used what we call an islands technique, where we looked for websites that were essentially visualization communities and then mined visualizations from those websites. And in that way, you can instead focus on subsets of the web where you can get more bang for your buck, basically. For example, you could go to the Plotly website and mine visualizations there. You could go to blocks.org, which is like the sandbox for D3, and mine websites there, or fusion charts. So again, here's an example of the kinds of visualizations that we mined from blocks.org for D3. We also looked at 4 other websites: Chartblocks, Fusion Charts, Plotly, Graphique. We won't go into them in detail here, but here's some pictures just to give you a sense of what we saw. And what you might notice is that there's a lot of overlap in the types of visualizations that people create across these websites. So we didn't necessarily isolate for specific use cases when we picked websites. Okay, so just talking a little bit more about the results of the crawler. Again, wait, did I say? Okay, so we visited 2 million. I'm sorry if I said 20 million earlier. Wait, it was 20 million, wasn't it? Anyway, I'm pretty sure it was 20 million, and that's wrong. It's actually a bigger number. And we only extracted 10,000 pages, 10,000 visualizations. In contrast with the island search, we got 4 times as many visualizations and crawled way fewer pages. So this got us a lot more examples. And in this case, you see a difference in the visualizations extracted versus pages visited for the island search, because on blocks.org, it really is a sandbox. Not everything people create in D3 is actually visualization. Sometimes you see a squiggly line because people just want to make sure they know how to draw lines in D3. We could debate as to whether or not that should or should not be labeled a line chart, but for our purposes, that wasn't a line chart. Okay, and so just talking a little bit more about the results of the crawler. So we extracted visualizations from these 5 different sites. You can see here that the majority of those visualizations were actually from Chartblocks. We extracted over 20,000 visualizations from that site, whereas the most unique number of the number of unique types was greatest for D3, where we saw over 20 types versus like 15 or 10 types, or even 4 types in the case of Chartblocks. Okay, so now the annotator. Now that we have these tens of thousands of visualizations, how do we actually label them? Well, what we do is we look at each of the SVG files through code. We collect basic statistics, and I'll talk a little bit more about what that's like very soon. And then we pass these statistics to an off-the-shelf classifier, and then we label them just by visualization type for now. And what does that mean? We just take these different images, for example, the ones you see on the slide, and then just say this is a bar chart, line chart, scatter chart, map, etc. Okay, so more about these statistics. Well, what you can do is you can take some basic SVG elements, such as circle elements, rect elements, line elements, path elements, or text elements, which have properties embedded in them, such as x, y, circle might have a radius, line might have another x, y to show you the start and end points, etc. And we can just inspect those properties for these elements, and then in this case, we can just say count up the number of each element we observe for different visualizations. So for example, in this case, for visualizations that tend to have axes on them, we'll see a lot of maybe lines and a lot of text. 4 axes, lines, and then labels for the ticks. But for different visualization types, you'll also see variance in the frequency of different element types, such as a scatter plot might tend to have a lot of circles, bar charts might tend to have a lot of rectangles, and lines and maps. Since you're drawing maybe more sophisticated lines, you might see a lot of paths. You can also dive in and calculate more statistics that are still pretty basic, but are starting to get into more interesting things like unique X position, unique Y positions observed, the minimum size observed for that particular element within a visualization, or the maximum size. We calculate over 100 statistics in the paper, but I'm not going to go through all of those in the talk, so feel free to see the paper for that. And here I'm just giving you kind of a sense of what we can do. So for example, in the case of bar charts, you'll see variance in the unique number of X positions, because you're going to have a different X position for each bar because you don't want them to occlude each other. But you'll see variance in the what it looks like to be the Y position of the bars, where we're calculating Y from the top instead of the bottom. and then you'll see variance in the minimum maximum size of the bars because we're using that as a for representing a quantitative measure. So that actually has semantic meaning here for that particular visualization. And then with scatter plots, you'll see a lot of unique X and Y positions, but in this case, you won't see any variance in the size of the circles, which is also an interesting thing that can be captured in the statistics. And then with maps, you'll just see a lot of variance, period, because maps are pretty complicated. All right, so a little bit more about our experimental setup. So we had to collect ground truth labels for every single visualization in the data set. This was pretty painful, hence the motivation for this project. And in this case, for websites that actually had metadata about the visualization types that were being represented on a page, we just extracted that through code. For the other cases, where there are definitely thousands of remaining cases, we had to manually label them, and the co-authors did that. Then we used a random forest classifier to do the training based on the statistics we collected, and we used 5-fold cross-validation to do the evaluation for our machine learning model. So our results were pretty good, actually. So across all the 5 websites that we looked at, we trained and tested. So we did 5-fold cross-validation individually first for each of those websites. And you see that the accuracy ranges from over 80% accuracy to almost like very close to 100% accuracy in the case of chart blocks. We also created a mixture data set where we had we took basically equal numbers of samples from each of the data sets and then also tried to balance for visualization type, and we still get about 85% accuracy. Oh, I'm jumping ahead of myself here. In the case of D3, where you see the lowest accuracy, it also had the largest number of labels that we had to classify against, so 22 different types. And even in that case, with the greatest variety, we still had pretty good accuracy. And just to reiterate, across all of the collections, we were able to get 85% accuracy. So just talking a little bit more about the annotated data set, we also did a little bit of analysis on it. We found that for most of the websites that we looked at, so this is not necessarily representative of the entire web, because this was only 5 websites. But for the 5 websites we looked at, where we did actually have a lot of observations, we found that most of them only had about 15 different types on them or less. And the only one that was the exception was D3, which makes a lot of sense, because that's an inherent part of D3's design, to support flexibility for a lot of different visualization types. And in this case, we found that 4 visualization types dominated across all of the collections: bar charts, line charts, scatter plots, and maps. And we found that about 65% of the D3 data set was these 4 types. In the case of graphic, over 90% was these types. So most of the time, you should probably pick one of these. Surprisingly, pie charts were rare. We thought we would see a lot more of them, but across all the collections, we found that they represent only less than 5% of the data set. So at least for our data set, this whole use pies versus don't use pies thing seemed to be a non-issue. So some takeaways. So it's pretty clear that from this, it would be helpful to have tools supporting a small number of visualization types for ease of use, since most of people's cases, at least that we observed, fell into these 4 visualization types. And that might facilitate, making it really easy for someone to quickly create a visualization. And in general, that would also support the idea of having a spectrum of visualization tools. So you have D3, so you can do exactly what you want to do no matter how complicated it is. But if what you want to do is super simple, then there should definitely be tools for that. And there are, but validation is good. And we observed that, at least in the D3 data set, that for the more obscure or more complex visualization types, when people would use them, when we would look at the examples of usage, they were often very similar to the gallery examples, where someone basically figured out how to rip out Mike Bostock's data and put in their own. And that was really interesting. So if you have examples, people will use them if they think it makes sense. All right, future work. So some things we're interested in. We want to scale this up. 5 websites is not web scale. We want to do web scale, so that's important to us. Also, websites are pretty rich. All we did was extract visualizations. We could extract more. The code, the surrounding text, other related images that might be on the page or the website. We could really push this to do more complex analysis across different data set types. It'd be amazing to capture interactions. How do we capture the fact that different interactions are being supported in a visualization, and also how might we learn design preferences automatically from these kinds of data sets. All right, so in summary, we crawled millions of pages, extracted tens of thousands of visualizations. We managed to automatically label them with basic statistics plus machine learning techniques and got pretty good accuracy. We analyzed this corpus and found that 4 visualization types pretty much dominate across all the data we collected. But if you provide examples, that's really helpful for using more obscure visualization types. And the data is actually available now at this website. So if you want to use it for whatever you want, feel free. You can download it. It's like 6 gigs, though, so you might want to be a little cautious. Maybe don't do it on the conference network. And I'm ready for questions.
Thank you, Laura. Thank you for being on time. So now we have time for some questions. Can you come up to the microphone?
Hi, Thomas Grice, Igneous Systems. This was really cool. How did you exclude? Did you say that you excluded like you said real users? Do you exclude tutorials and things like that?
So we basically would go to a website and then just mine everything we could. Okay. We wouldn't necessarily exclude things. So, for example, we didn't mine the D3 gallery because we just didn't go directly to the D3 gallery and mine those examples. But if they are stored at blocks.org, then we picked them up anyway.
Okay. And what you said you used SVG. Were there any other formats that you would have liked to use?
So it would be really nice to say pick up any and all formats that may have a visualization in them. Something that we would love to have done was say identify and download Excel files and check if they have visualizations in them. That's definitely something of interest. But to kind of mitigate the work to benefit ratio there in terms of actually getting visualizations, we chose to filter using scalable vector graphics. It also provided nice structure for our machine learning model, because when you have a lot of structure and information about the objects in the output, you don't necessarily need really fancy techniques to extract that or simulate that. But in the future, we would hope to expand this. And there's existing work on raster image classification for visualizations that I just didn't mention in this talk.
And one more question while you guys switch.
Hi. Okay, I'm Carney from the Hebrew University. I have a question about the takeaways. You said that you may need more tools to simplify those particular 4 examples that were more prominent. I would like to ask, maybe it's because the current tools make it simple to do those specific visualizations that they're more prominent?
That is a good point. So we just collected the data and kind of commented on what we observed from the output. We didn't necessarily dig deeper to thoroughly investigate the reasons behind why those particular visualization types were prominent. But it's possible that across all 5 of the websites that we looked at, they intentionally designed their tools to make those particular types easiest to do. For example, with Chartbox, they only supported 4 visualization types, so that made it fairly straightforward to use that particular tool.